This is Mrs. O'Neill for AP Chemistry, Chapter 4, Section 4, Oxidation-Reduction Reactions. Boy, is that a mouthful. That's why we call these redox reactions. You should have watched the intro lesson on redox reactions, and here are my notes. He talked about what redox means. Well, it's a combination of reduction and oxidation. In other words, it's just transferring of electrons. Gave you a nice flow chart as he always does, and he talked about these electrons moving always from oxidation to reduction, always from the oxidized substance to the reduced substance. How do we remember this? Oil rig. And I'm going to give you two other ways to remember this as well. So here's the example he gave. He talked about the reaction hydrogen and fluorine making hydrogen fluoride. By the way, this is hydrofluoric acid. That's the other way of saying it. And it is weak acid. HF is a weak acid. So anyways, hydrogen is being oxidized because it is losing those electrons, and fluorine is being reduced because it's gaining those electrons. So we can look at those half reactions and figure out which one's being oxidized and which one is being reduced. He talks about oxidation numbers and the rules and how to assign every single element a charge number. So of course your elements are always going to be 0. Your ions are always going to be the charge like that you see on the periodic table. So for instance, your sodium should be +1 because it's from group 1. Your chloride is going to be -1 because it's group 17. Oxygen, however, is almost always -2 unless it's in a peroxide, and we'll talk about that later on. And hydrogen is almost always +1 with nonmetals and -1 with metals. Yes, you can see sometimes hydrogen is going to be a hydride. And number 4, in neutral, the sum is 0 or charge in ions. What he means by that is if you have a compound, the whole thing has to equal 0. So you have to get these charges to equal 0. And we're going to see how in the heck are we going to get the charge of sulfur here, knowing that the charge of the whole compound is 0. Same thing with this polyatomic ion. How do we find the charge of sulfur here when the whole polyatomic ion has a -2 charge? He gave an example of magnesium with hydrochloric acid forming magnesium chloride and hydrogen gas. Well, here the magnesium is being oxidized because the charge is getting bigger. Here the hydrogen is being reduced because the charge is getting smaller. Well, what happened to the chlorine? Well, I will tell you that with almost all redox reactions that I've ever seen, there's only ever one element that gets oxidized and one element that gets reduced. Even if there is a third, fourth, or fifth element, those elements, their charges stay the same, which means the electrons are not being transferred within those particular elements. So again, those half reactions are going to be helpful. In an oxidation half reaction, the electrons are lost, so those electrons are going to appear on the product side. And in a reduction reaction, the electrons are being gained, so those electrons are going to be on the reactant side. So he gave you some practice as well, assigning all of those elements a charge number. And then he said, well, let's see which one's being oxidized and which one's being reduced. Well, here the manganese is being oxidized because it's getting bigger in charge. The lead is being reduced because it's getting smaller in charge. So there's that. And then he talked about the half reactions. Well, what does that oxidation half reaction look like? Well, oxidation loses electrons, so the electrons are going to be as the product side, and the lead is reduction, so it's going to gain electrons, and those electrons are going to be as the reactant side. So again, we'll get into more detail, especially when we talk about titration and when we get into electrochem, which is towards the end of the course. And other applications would be fat in food and octane in gasoline, just a little extra stuff he kind of puts in there. So back to your packet of notes. Your objective is going to examine a reaction in which electrons transfer from one reactant to another. So why are these redox reactions so important? Well, This is going to be hours. How are we going to balance complex chemical reactions? And also use pH meters later on. So again, you might want to pause the video and fill in the blanks and then play to hear my words. So again, you're going to hear redox a heck of a lot more than oxidation reduction, because that is just a mouthful. So corrosion is a type of redox reaction where our nice, beautiful copper Statue of Liberty has now turned into copper oxide because that copper is being oxidized with the oxygen in the air. I will tell you, however, redox reactions do not always need oxygen to get oxidized, okay? So we went over this. I've said this now a few times. Now just make sure it gets into your notes. How are we going to remember this? Leo the lion went GER. You can remember loss of electrons is oxidized, gain of electrons is reduction. Or he liked oil rig. Oxidation is loss of electrons, reduction is gain of electrons. Or I like this one the best. If you think of a box, especially when you're opening one as a gift, your oxidation number gets bigger. It's oxidized. So I like to remember box. Oxidation number gets bigger. It is being oxidized. So yes, you need to keep track of those electrons by assigning all elements an oxidation number or a charge number. They mean the same thing. You need to be able to do that and look over those rules on page 132, as well as, Mr. Bozeman's science rules, and of course we'll do some practice problems. So in an oxidation-reduction reaction, again, redox, you need to assign those oxidation numbers because that oxidation will change in some way, right? That's why it's redox. That element is going to change from one charge to another charge because those electrons are being transferred. And remember, they're being transferred between those two reactants at the same time, So let's look at an example here. We have sodium plus chlorine to make our sodium chloride. Let's assign those oxidation numbers. Well, sodium on the left will be 0 because it's an element. Sodium on the right is going to be +1 because now it's in a compound and it is attracted to the chlorine. So now the chlorine goes from a 0 charge because it's an element to a -1 in a compound. So Leo the lion went GER, or box, however you want to think about that. Which one is losing electrons is going to be oxidized. Which one is gaining electrons will be reduced. So in other words, if it's being oxidized, it's becoming more positive. It's being reduced, it's becoming more negative. So this one's pretty easy, right? You're going from 0 to a +1 and a 0 to a -1. So the sodium is being oxidized and the chlorine is being reduced. Another way to think of it is most of the times, your metals are going to lose electrons being oxidized, and most of the time your nonmetals are going to be gaining electrons, so they're going to be reduced. Now, you will see, however, there are some equations where it's all going to be nonmetals, so then you got to figure out which nonmetal is being oxidized and which nonmetal is being reduced. So just play it safe and label all oxidation numbers. So see if you can come up with the two formulas of these compounds and come up with that oxidation number of nitrogen in both compounds. Hopefully you got that as your compounds. If not, pause and now come up with those charges. That nitrogen should have been easy because nitrogen's in group 15, so we'll have a -3 when it's nitride. Now that guy might be a little bit trickier. How did we come up with that? Well, here's a little bit of algebra, okay? So we know that hydrogen's +1. We're looking for nitrogen as an X, and we know that oxygen's a -2. We also know that the whole compound is a 0 charge because it's a compound, right? It has a neutral charge. So let's add these up, a little bit of algebra. So there's one H with a +1 charge. There's one nitrogen, so that's +X, and there are 3 oxygen with a -2. So 3 times -2 gives us that -6, and that's all going to equal 0. Rearrange, do a little bit of algebra, and you get a +5. Or you could have just looked at the polyatomic ion, the NO3 nitrate, by itself. But if you do it that way, just remember that now that polyatomic ion does not equal 0. It now equals -1. So see if you can come up with the charges of all 4 elements in this compound. There's our X, and do a little bit of algebra. Hopefully that makes sense. So you have 1 plus 1, you have 1 plus 3, you have 2 X's, and you have 4 times 2 times 2. So you got 4 times 2 is 8 times the 2 to give you that 16 overall charge for oxygen. And again, rearrange and solve for X to get that plus 6. Or you could have just solved for the polyatomic ion, because really sulfur is the only charge here that you really probably weren't sure of, and still use algebra to get your plus 6. Okay, so now you have an activity series, and that is dealing with single displacement reactions similar to your double displacement reactions, and this is going to help us predict if the reaction even happens. So we do not have to memorize this activity series. I'm going to show you on the next slide, but you do need to understand that the top element is the most reactive, meaning that it wants to be in a compound the most, and the bottom element is the least reactive. It wants to be alone. So you will never have to memorize this list. However, you will need to be able to understand it if they give you some kind of list. So you always want to remember the bottom, and I like to remember it this way. AU, which is gold or silver. We wear gold and silver jewelry all the time. They like to be alone. They like to be by themselves. They like to be as an element. So if they are already as an element by themselves, the reaction probably will not happen. However, if you have somebody like lithium or barium or sodium, they're really reactive. They want to be in a compound. They want somebody to bond with. So if they are alone as a reactant, most likely the reaction will occur because they want to be bonded with that negative anion. So this might help you to use a real periodic table, which if I haven't given you one yet, I will remind me, and I will. But it's that nice colorful one, and they give you the bold charges, which is usually the most stable, and that's the one you're going to use. So here's an example of 2 single replacement reactions. Will the reaction occur? Again, either go back to that slide to look at that activity series, or look in your book. So let's look at here. A, iron is more reactive than the copper, so the reaction will take place. So you're going to, again, almost like your your double replacement reactions, really what's happening here is your 2 positive components are going to switch places. So because the iron is more reactive than the copper, it's higher on that list. Iron wants to be in a compound, iron and copper wants to be by itself, right? Again, you know that there is copper jewelry out there. However, it says lead is more reactive than the silver. Well, silver was already by itself and lead is already in a compound, so there's not going to be a reaction occurring. So see if you can come up with these 2 answers. Pause the video and again look at that activity series. Okay, so hopefully that makes sense. Now, we want to remember about reactions. You always want to balance, 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 and you always want to label the states, especially solid, liquid, gas, and aqueous. That's going to help you decide if the substance stays as is all the way through the reactions, or does it break apart into ions. If it's a strong substance, again, you're going to use a regular arrow, and strong acids and bases are on the list. Weak substances, you're going to use the equilibrium. And they stay as a molecule all the way through on your reactions. And of course, your solids, liquids, and gases also stay as is. We talked about this before, so you can read over that again. And we want to remember that your types of reactions are going to be your precipitation or neutralization reactions. We want to remember strong versus weak. We want to remember redox and checking those charges. And that single replacement reactions, again, we want to talk about that potential list. It's called that reduction potential list or that activity series list. And of course, the one that's most reactive, I want to bring this to your attention. If they give you a reduction potential list, the more reactive one is on the bottom. See you in